Okay, so if I want to write an equation that has the following characteristics, if I've got a vertical asymptote at x is equal to 5, that means in the denominator, that's going to be a vertical asymptote. The associated factor would be x minus 5. If I've got a vertical asymptote of -5, then a factor in the denominator would be x plus 5. If I've got an x-intercept at 2, that's the same thing as a 0. If I have a 0 at 2, then x minus 2 is a factor in the numerator. And if x equals -1 is also a 0, then x plus 1 is a factor. Okay, so that's what my thing would look like. And that's going to make the general shape, but then maybe it has some sort of intercept like this. Well, to make this intercept happen, I'm going to need a constant out front. Okay? And that's what my polynomial is going to look like, is something like this. So to make this intercept happen, I see that when I plug in 0 in for all these x's, when I plug in 0 in for all of these x's, I hope that I end up getting out 4. And if I didn't have that k there, what I'd get on top would be -2 times 1. On bottom, it's going to be -5 times 5. What I'm going to have, if that k wasn't there, would just be a -2 divided by -25. In other words, 2 over 25. And you can clearly see that 2 over 25 is not going to be equal to 4. That's why I need that k there. That k is going to allow me to put a number out in front of my function to force it to go through this x-intercept. So when I multiply both sides by 25, I get 100 is equal to 2k. When I divide by 2, I get 50. So my polynomial is just 50 times x minus 2 over x plus 1 divided by x minus 5, x plus 5. That would be a polynomial that does those things. It's not the only one, but it's one. I'm sorry, a rational expression. So maybe I should call this r of x. I don't mean a polynomial. I mean a rational expression, which is actually the quotient of polynomials. Okay? All right. So if they ask me to find same sort of deal, find some sort of a rational function that does this thing, well, because I have a vertical asymptote at x equals 3, that means in the denominator of my expression, I'm going to have an x minus 3, so that it forces a division by 0 at 3, which is what makes it blow up. More than that, because it blows up in the same direction, or in other words, since it acts like 1 over x squared, that means I'm going to have a squared power here. Right? Well, then over here I have a vertical asymptote at x is equal to -3. That means the associated factor is going to be x plus 3. But notice, as you walk towards that asymptote, you either have to explode up or down. It explodes in different directions around that asymptote. That means it acts like 1 over x, or some sort of an odd function, so I'm going to put it to the 1. So because this is squared near that asymptote, it's going to go in the same direction. Because this is to the first, it's going to go in opposite direction. So I'm pretty happy so far. Then I know that I have a 0 right here at 2. So that means in the numerator, I'm going to have an x minus 2 as a factor. More than that, it crosses there. So I know that that thing's going to be maybe to the first would cause that. Maybe it's to the third. Maybe it's to any odd number. So I'm just going to put to the first. Okay? I'm not looking for the exact graph, just one that does this. So we've accounted for all the properties we have so far. We also see that as x gets really big, the end behavior of this thing notice it looks like it settles down to 0 in both directions. Since the degree of this thing, you're going to do a little note. Since r of x equals x plus a bunch of crap on top and an x cubed plus a bunch of crap on bottom, y equals 0 is going to be a horizontal asymptote. In the long run, since the degree of the bottom is bigger, it's going to pull the whole thing to 0. So we are good in that we are doing the correct end behavior. So the last thing we have to do is make sure that we go through this point right here, and that point is 0, -2. To do that, we have to introduce a constant out front. So r of x is equal to some constant x minus 2 over x minus 3 squared x plus 3 would be a function that does what we want. Specifically, what we want is when you plug in 0, you get out -2. So here, I better get out -2 when I plug in 0 here, here, and here. So I get -2 is equal to what? -2k over 9 times 3 is 27. So if I divide both sides by -2, I think it's clear that 1 is equal to k over 27. In other words, k is equal to 27. Thus, our rational function is just 27 x minus 2 over x minus 3 squared x plus 3. Again, that is not the only rational function that looks like that, but that's definitely the lowest degree. So that's 59. Let's look at 61. Same sort of reasoning. I've got a 0. What did I start off with over here? -2. So since I've got a 0 at 2, since that's an x-intercept, that means that in my rational expression in the numerator, I'm going to have an x minus 2. Since it crosses locally, that means it wants to act like x, so it's going to be some sort of odd number. So I'm going to put a 1. Nope. We also have a 0 over here at -3, so that means x plus 3 is a factor. And since it crosses there, I think locally that's going to be raised to the first. But then I have a vertical asymptote at x is equal to 1. That means x minus 1 is a factor of the denominator. But notice here, it acts like 1 over x near it by going in different directions as you approach the asymptote. So I think that that might be to the first. So maybe I say x-intercept. Maybe I say x like x. And over here, it acts like x. Some odd thing, right? So that's my polynomial. But then, for my y-intercept, I need to take my thing and introduce this constant up front to force it to go through the point 0, 2. So watch what I do. To go through 0, 2, we need to introduce this constant and specifically have that when you plug in 0 for x's, you better get out a 2 for your y. And that means k better be equal to -6 over -1 is 6. So in other words, k is equal to 1/3. Therefore, my rational function is just 1/3 x minus 2, x plus 3, all that stuff over x minus 1. That's it. So that's 61. Now we've got 81 and 82. Okay, refugee camp at a hospital. Large mixing tank. I got 300 gallons of water into which 8 pounds of sugar have been mixed. So I'm going to let this be water. I'm going to let this be sugar. So originally I had 300 gallons of water and 20 pounds of sugar. Tap is open and 20 gallons per minute of water is introduced, and 2 pounds per minute of sugar is added. Find the concentration after t minutes. Well, the concentration is just the amount of sugar divided by the amount of water. So it's going to be, what? 20 plus 2t divided by 300 plus 20t. And that would be in pounds per gallon. Yes, you might simplify that by factoring a 2 out of the top, and you'd be left with 10 plus t. If you factor a 2 out of the bottom, you're left with 150 plus 10t. Since those 2's can now cancel out, you're left with 10 plus t over 150 plus 10t, again, pounds per gallon. And now if I duplicate that page and go to the second page, I can answer the next question right here. It says you got a patient's bloodstream and this is the concentration where T is time in hours. It says what happens as T increases. So in other words, it wants to know, is there a horizontal asymptote? Because it's asking about in the long run, what happens? We know that in the long run is just a horizontal asymptote. So if you have 2t over 3 plus t squared, well, as t goes to infinity, the top wants to be 2t. It dominates because it's the only term. And then the bottom t squared dominates. I think you can quickly see that that's equal to 2 over t, and in the long run, that goes to 0. So, c equals 0 is a horizontal asymptote. Thus, in long run, comma, concentration goes to 0. Great work.